In this video, we will talk about Ldpc error correction code and OFDM modulation in a wireless system. Previously, we recorded a series of demos, and you can see them at the link on this slide. So in this demo, we will concentrate more on the integrations of Ldpc code with OFDM in an emulated environment. Okay, and Ldpc is about low density parity check error correction code, and it's used in advanced wireless applications, including 5G, Wi-Fi, WiMAX, digital TV, and satellite communications, and others. It supports high data rate, and its algorithm is very efficient. It's good for use in applications where the environment has a great deal of background or data corruption noise. This diagram shows you the internal of our implementation. It consists of an encoder on the top here and a decoder on the bottom here. And on the left-hand side is the input data stream and then the output data stream. So on the encoder side, the code take in one packet at a time or a block of data at a time, and it feed that into the encoder core, and then it generate the data out and send out to what we call the remote port to interface to the OFDM subsystem. So what we have done here is we also add the ability for the user to configure the kind of information that they feed in and the kind of encoding that they want to achieve. And we also have a capability for the user to inject errors or configure the probability of the errors. So this is intended to show on the receiving path when the data is coming back, we decode it, and then we able to correcting it, and then we want to compare the original source with the receive validated data so that we can cross-check them to make sure that the Ldpc function does what it's supposed to do. Okay, so on the right-hand side here is the interface to the OFDM subsystem for transmitting and receiving, and I'll explain that a little bit later. There are a couple of references that I want to point out. One is for Ldpc, the other one is for OFDM, which is orthogonal frequency division multiplexing. Okay, and the video is too short, so we cannot explain the other details. But you can find them at those videos. The way we do this demo is we constructed with two separate systems rather than one, because simply now the system just grow with a lot of code. Okay, and on the left hand side here, you see this is a Ubuntu system, and we implement a concept called a remote port, and that go over to another remote port. And on this side here, which is the right hand side, is a window-based system that run a simulator. Okay, and on this side here is the Ubuntu system, which is Linux, and it run an emulation system. And on the emulated ARM CPU function, we created a user app called the Ltransfer, and we implement Ldpc code as well as the wireless relay functions, and it includes embedded version of Linux and several other things. In this system here on the right, we implemented essentially is a hardware simulator for FPGA in this case. So it can simulate Verilog code, whereas on this side is mostly C code type of function. On this side is Verilog type of functions. And we implement OFDM in Verilog code. And we also created a wireless channel loopback. Okay, so there's a lot of code, and we we want to use low cost type of PC system, and this mechanism allow us to separate things out and able to keep the performance up. So you can see that the on this side here, where we have the OFDM code, and this has been explained in the previous video where I give you the reference. And there's a lot of code here, and it run typically much slower than what you can run on a C-based type of system. And by doing what we're doing, by separate the functions out, we overcoming the performance bottleneck of low-cost systems. I'll explain a little bit about the demo itself in the setup, so you can see when the engineer explained it to you. There are primarily 3 windows. On this side here, where it shows the waveform, that is where we have the OFDM wireless transmit receive loopback. It's a hardware simulator, and in this case, it's Vivado. So this represents it's a Windows side, and it represents the FPGA simulator. And on the right-hand side, there's 2 windows. The top window here run the emulator, which actually run on the emulated ARM subsystem. And on the bottom here is the remote port monitor. So it monitors what's going on when data is being transferred across the remote port. Okay. So on this side is a Linux-based ARM processing system. And in the demo, you will see a setup like this, and you will see things being active as the demo is running. Okay. So the next part here will be the demo itself.
In this video, we will demo the OFDM-based wireless file transfer using Ldpc error correction code. This time we will be introducing small channel error to the transmitted data, and we will see the ability of file transfer program to correct those errors and retrieve the original file. In this setup, on the left side we have OFDM simulation environment up and running. Using simulation script, I have set up transmitter and receiver ports to transmit and receive the OFDM frame data from the wireless emulator. On the right side, I am running a OFDM remote client program, which will establish connection between emulation platform and hardware simulation to transmit the OFDM data. On the top right window, we have wireless emulation environment up and running, where we will run the file transfer program. Now in the program directory, we have an input text image file called flag.txt, which we will be sending using OFDM file transfer. Now let us run the Ltransfer Ldpc program. This program takes the IP address of OFDM simulation environment and its command line arguments, along with the port numbers for transmitter and receiver. And finally, the file name. Now user is given a choice to select the error correction mode or disable it completely. For the first run, we will disable the error correction. Then we need to configure the error probability in the transmission channel. We will set it to 0.02, which is equivalent of 2% bit error in the transmitted data. Now we have error correction disabled, so we can start the transfer. Now we can see the configuration of OFDM transceiver, which was explained in the previous video. Now we are ready to transfer the data using OFDM simulation. So let us start that. As you can see in the left window, the OFDM simulation for each frame is running. Also, another thing to notice here is that the file size for the OFDM transmission data is 814 bytes, which amounts to just one packet, and we will be sending total of 3 frames. Now we are waiting for the last frame to be sent and received by the simulation. So now the OFDM file transfer is complete. And you can see we have sent and received 814 bytes. In the channel simulation, we have introduced the 2% channel error as specified before. And in the output file, we have retrieved the output underscore flag.txt as a retrieved file. There is in the data validation step, you can already see there are invalid bits present in the retrieved data. And the final bit error rate comes out to be 0.02, which is approximately same as the channel error that was introduced. We can also use diff command to see the difference between input and output files. Or we can visually check that the output file is different than the sent file, which is a distorted form of the sent file due to the bit errors present in the data. Now we will run the same program using the Ldpc error correction. Now in this case, we will select error correction mode as Ldpc. Now here user needs to configure the Ldpc error correction block by specifying the number of encoded bits per block, which we will set to 800. And out of those 800 bits, we need to specify how many information bits will be present per block, which we will set to 480. Again, we need to configure the transmission channel error, which is 0.02 or 2%. Now, in the Ldpc configuration, you can see that the encoded block size is 800. Out of those 800, 480 are information bits, and the remaining 320 are the parity check bits, which are used for the error correction in the decoding phase. Now we are ready for encoding. As you can see, the program follows different steps in encoding, including parity check matrix creation, generator matrix creation. It creates a binary source file, which is then encoded into 14 encoded blocks, each of 800 bits. Then we do the data conversion to convert the file into OFDM transmission file of 1400 bytes. You can see the OFDM transceiver configuration again. And now we are ready to do OFDM transfer. So we have transmitted the OFDM data to the simulation environment. We can see the frame by frame simulation of the entire transmitted packet. If you remember, the previously OFDM transmission data size was 814 bytes. That was same as the input file size. But this time, we will be sending 1400 bytes of data through OFDM transfer. This is because of the code rate. Since there are additional parity check bits added with each 480 of information bits, we are able to achieve the code rate of 0.6, due to which the total size of data being actually transmitted through wireless OFDM channel is increased to 1400. As you can see, we have received all the data from the OFDM, and the data conversion step converts the binary data for the channel simulation. And in the channel simulation, we introduce the specified error. Now we are ready for LDPC decoding. So we'll start the decoding process. So now the program operation is complete. We have successfully decoded and retrieved the output file. So we have used the probability propagation method for LDPC decoder, and it was able to decode all the received 14 blocks, and it was able to also revert back all the bit changes that were present due to the channel error. In the data validation step, we can already see there are no more invalid bits present in the received data, and the final bit error rate is 0. We can verify this result by comparing the input and output files again. You can see they are exactly the same, and we can see that the output file is same as the one that was sent. So in summary, we have successfully demonstrated the OFDM file transfer and its ability to correct the bit errors in the transmission channel using LDPC error correction method. Thank you for watching.